a combination of geothermal geotubs, which is geothermal heat pumps combined with thermally activated building systems. And this geotubs concept again combined with secondary heating and cooling emission and or production systems. And in the movie you should have seen that this concept includes a number of advantages. The tubs being a radiant heating and cooling system that can deliver a high levels of thermal comfort. The geothermal energy, which is a sustainable energy energy source, and because of the combination with tubs, which works at very rather low heating and cooling temperatures, it also can reach a high energy efficiency. Furthermore, if we start combining geotubs with secondary heating and cooling systems, it can also be interesting in terms of financial costs, in terms of optimizing the balance between the different energy sources. And therefore we might or could conclude that maybe more buildings than today, or well, every building might be a lot, but more optimize, improve the performance of hybrid geotubs. Secondly, to demonstrate its performance, to demonstrate geotubs buildings and the innovations made during this project, to assess the performance of hybrid geotubs, and finally to also take away barriers that would take away the barriers that prevent hybrid geotubs from being more largely implemented in various European countries. So, as I said, we brought together a multidisciplinary consortium consisting of partners from the industry, from small and medium-sized enterprises throughout Europe, and from academia, together with also the European HVAC Association, RIVA. All of us together as a rather motivated team, of which a large part you can see here, are working together on this project. So the Hybrid Geotubs project is a Horizon 2020 research and innovation action, which is funded by the European Commission. It started in September 2016, and soon we are going into our last year, in which all the pieces of puzzle we have been working on will fall together into results. So I'll go deeper. I'll give you a quick overview of the many aspects that are going on in this project, and I'll start with the part on the optimization or improving hybrid geotubs. One part of that is the optimization of the design of hybrid geotubs buildings, and there we are working on a better optimal sizing and integration of the various system components in hybrid geotubs. And therefore, by doing that, we are aiming at an optimization of the energy efficiency of the system, the comfort, and the financial costs. This will lead to a design methodology that should allow a short and straightforward design phase, and therefore also reduce the design costs and efforts that are needed today by consultancy or engineering offices. And all this work should result in a new hybrid geotubs handbook and tools for feasibility study and pre-design of hybrid geotubs. More detail on this you will hear later presentations today by Wim Boydens and Jelle Laverge, so I won't go in detail here, and I'll go to the next topic, which is the optimization of the hybrid geotubs during operation by use of a better way of controlling the system. So in this project we use model predictive controls for optimizing energy efficiency or CO2 emissions or costs, energy costs, while taking into account the good comfort to be maintained within a hybrid geotubs building. And it is estimated, we are still doing research on it, but it is estimated that by using these model predictive controls instead of the more classical control approaches, energy use reductions between 10 and 25% could be feasible. This is something we are assessing throughout the project, so we hope to have more definite figures of this in 1 year from now. Also, the setup of model predictive controls is a challenge, and therefore our partners in the project are developing a model predictive control toolchain that allows semi-automated development of the control, so that the setup and the making of the control becomes less difficult, and also take into account the startup of such controls, the adaptiveness, robustness, and so on, in order to reduce the development and commissioning efforts. This is something we will not address today, but people who are interested in this can always contact Lieve Helsen, because she will be able to tell you everything about it, or refer to her PhD students. Okay, that were the main aspects of the optimization in the project. Let's go to look to the demonstration. There we have a number of demonstration and case study buildings throughout Europe. We have there 2 office buildings, one in Belgium, one in Luxembourg. We have an elderly home in Belgium as well, a multi-family building in Zurich, Switzerland, and a school in the Czech Republic. These buildings are GEOTABS buildings. 3 or 4 of them will be implemented with model predictive controls, or 2 of them already have the model predictive controls today, and using these buildings we are assessing the performance of this system. So the demonstration and case study buildings are used to demonstrate hybrid GEOTABS. For example, here you can see an example of the energy dashboard developed by one of our partners that shows the actual energy use of the system yesterday actually. We can also use it to implement the model predictive controls and to test the design method. And then of course, after having all of this, we assess the performance of the buildings in real-life measurements. So we have a number of KPIs there, performance indicators that we are looking at, including energy performance of course, and environmental performance. Also indoor environmental quality, health and productivity are assessed. You will learn more about this in one of the next presentations, and also financial costs are of course considered. Apart from the real-life measurements in these 5 buildings, we also have a virtual testbed that is a testbed of emulator models that we also use to assess the performance of the system, to compare it to baseline, more classical or more traditional heating and cooling systems, so that we can see what the actual improvement is by applying this concept. And then we zoom out from the demo buildings towards entire Europe to assess the feasibility and performance of the hybrid GEOTABS concept, not only in the regions where our partners are from, which is, well, we cover the most of Europe, so we look to various European climates, from the warm Spain to the more northern countries and the intermediate countries, and we focus there on the building stock for schools, multi-family buildings, offices and elderly homes with a size higher than 1,000 square meters gross floor area. By looking there also to the people, planet, profit, so the same KPI, we will obtain a cost-benefit analysis that can then be further used. And that brings me to the exploitation, or our will to take away barriers that would prevent the hybrid GEOTABS concept from being implemented much more than today. So, of course, the cost-benefit analysis and market analysis together will lead to a business plan that, especially for the industrial and SME partners, can help them to use the concept more. Further, apart from that, we are also looking to industrialization strategy. So we're looking to the different components and elements within the hybrid GEOTABS system, seeing whether they can be pre-engineered or prefabricated, so that the whole building process can also go more easy. An example you see here is the enhanced geothermal response test that was developed by one of our project partners to improve the sizing of borehole fields or ground source heat exchanger in the hybrid GEOTABS concept. Finally, they also look to broaden the application. Geotabs is typically applied in new buildings. However, there exist solutions for renovation as well, and one of them is being investigated by one of our partners and will also be explained later today. And therefore, this can help us to broaden the application range of geotabs for buildings. So, as a conclusion, via this work of optimization, demonstration and exploitation, we hope to bring hybrid geotabs closer to the European market and therefore also improve sustainability and energy performance of our building stock. As I started, we hope that every building in the future might deserve its share of geotabs. Last but not least, we also would like to share geotabs with all of you. So you're very welcome to find us via social media, our website or our newsletter, where you can follow everything we are developing and doing and follow our project. Thank you.
Thanks a lot, Eline. Now we all know what hybridGEOTABS is about. And you should know by now that the hybrid refers to a combination of geotabs and a supplementary system. In the first part of this workshop, we will focus on that primary system for distribution of heat and cold. So the thermally activated building system are the taps. And there we have 3 speakers. Now for the practical organization of the workshop, it's a workshop, it's not a lecture. So we would like to have some interaction when this is useful. We have a slot at the end where we can have an open discussion. So I suggest that those who have questions during the presentations, and it's more like a request for clarification, please interrupt the speaker and ask the clarification. If it's more like getting into discussion, please park this to the end where we have the open discussion session, such that they can bring the story and in the end we can have some discussion. Okay? The first speaker now is Ongun B Kazanci from the Technical University of Denmark. He will explain a bit more the general context on the environmental indoor quality, the benefits offered by radiant systems in general. And then we will focus, we will zoom into the taps, and then we will zoom into PCM ceiling panels. So we will have 3 presentations in this first part.
Okay, thank you very much for the introduction, Lieve. So I see many project partners, but I also see many people I don't know. So I would just like to see where we are with the audience. So how many of you have heard about this project before? Ah, great. Well, I mean, if you're from the project, I hope you heard about that. And how many are familiar with radiant systems? Like, Qian, it doesn't count, please. Okay, perfect. Doesn't count. All right, perfect, thank you. So I will talk about indoor environmental quality benefits, or I would actually say aspects of radiant systems. So there are basically 3 main parts in this presentation. The first part is about a little introduction to the radiant systems and a little bit about all air systems, so they're more convective systems. Then a little bit about what type of indoor environments they create and what we know about the indoor environments they create. And the last part of the presentation is about what we do in this project related to indoor environmental quality. So now this is maybe obvious because now we know this and we've had a few presentations about it until now, but it's important to remember what we do, why we do. So we as people, we spend most of our lives indoors. So having said that, the buildings, they're built for people and they're not built for saving energy. That's not the point. And the buildings, since they're built, well, they should also provide an indoor environment where they would promote a comfortable, healthy and productivity stimulating indoor environment. And it should be done preferably not at any cost, but at the cost where you use lowest possible energy use. And not just energy, and preferably with non-fossil energy resources. So that's where the actual heat or cool should come from. And heating, cooling, and ventilation systems in general, they allow us to create the indoor environment that we want in buildings. And now I'm getting into it, but we can just say that there are three main components or three main parts of each heating and cooling system. That is, first part is the generation, the second part is distribution, and the last part is the emission system, also known as the indoor terminal unit. So this is part of the heating and cooling system that is in the building, for example, or in the room, for example, the chilled beam like you have in this room. So, and indoor terminal units, just by definition, they are active building components that can emit or remove heat or moisture from indoor spaces. So that's what they are. And what they can do, it differs depending on which system you have. But for us, the most important for the sake of this presentation is that they have different heat transfer mechanisms. They rely on radiation, convection, or both. And depending on which terminal unit you have, you will get different indoor environments, or different indoor temperature, let's say distribution and air speeds, flow fields, and so forth. So, radiant systems, they work with a combination of radiation and convection. There are three main types of them. The first one is radiant heating and cooling panels, so they are detached or detached from the main building structure. Then you have the second part, or the second type of radiant systems, that are separated from the main building structure but embedded in surfaces. So for example, floor heating is an example of this. And the third one, also as you now with the tabs, more related to the project, is thermally active building systems, where you have the pipes actually embedded in the main structure of the building. So you can heat, cool, or activate the thermal mass that is available in the building. And they look like this. So for example, this is an example of panels. They're usually hanging from ceiling, so they're, as I said, detached from the main building structure. And you have examples of floor, wall, and ceiling. And then the last one is tabs. So there are also low temperature heating and high temperature cooling systems. It basically means that your heat transfer medium, which in this case is water, works with temperatures that are close to the indoor temperatures that you want to work with. So that's why the low temperature heating and high temperature cooling. And they have different heating and cooling capacities. I will not get into that. So this was the water-based radiant surface heating and cooling systems in general. Maybe, let's say, the more traditional way is to do it with air conditioning, or they're sometimes referred to as all-air systems. And they work with, as their name suggests, it works with full air. So everything that happens in the room, heat emission, heat removal, it happens with air. So you either provide cold air, provide warm air. That's how you regulate the conditions in the room. So everything happens with convection. There are different types, but the main idea, very briefly, is that if you have, let's say, if you have a mixing ventilation system, these are, let's say, the two main total volume conditioning principles. So if you have mixing ventilation, you're trying to, as the name suggests, try to create uniform conditions in the room. So you're trying to mix everything. So temperatures are uniform, contaminant distributions are uniform. In the displacement ventilation, in the middle, the idea is to provide, as again the name suggests, provide clean air. So you displace the existing air, so that ideally the occupants breathe fresh air, and then it's exhausted usually from an upper part of the room somewhere. So they are air-based systems. Everything happens with convection. Now, in practice, when you have different systems, how you operate them and the conditions you create differ. So normally, if you have an all-air system, you would have a temperature set point, you will have a certain deadband, so you will try to keep the temperatures, let's say, constant within that level. And not in every building, but quite often we see problems with all air systems or air conditioning systems is that they can create draft, noise, possible symptoms of sick building syndrome, and they would lead to usually high energy costs and high operational costs. And it's a little different than tabs. How tabs work is that they rely on creating, let's say, not such a constant condition in the room, but they let the temperatures drift during the day. So what does that mean? It means basically something like this. If you take a representative operation of one day, so this is 24 hours, In addition, let's say in contrast to all air systems where you have to cool as soon as there is a cooling demand, what you do with tabs is that you spread your cooling load throughout the day. And if you start from, let's say, in the morning, in this graph, you will see that the building is, let's say, cool. And as soon as the occupants come in the morning, so around 8 o'clock, you can see that the temperatures, they increase a little bit. This is mainly due to occupants arriving at work, internal heat gains becoming dominant. And then the temperatures would increase during the day, but not above, let's say, the PMV of 0.5. So that's the temperature drift. You start with lower temperatures, you let the temperatures increase during the day, but you don't let it, let's say, reach overheating. And here again in this graph, as soon as the people leave, the temperatures would decrease and you would start, let's say, cooling through in the night. And the main idea is to make sure that your room is cooled and is ready to absorb, let's say, the heat or the internal heat gains the next morning. So that's the main idea. I will save the slide for my second presentation, but one of the, or two of the benefits, or two main points of benefits of radiant heating and cooling systems is that since they don't really have a terminal unit in the room, they're integrated with surfaces of the room, they provide possibility of free use of space, no cleaning requirements, and quiet operation. So there's also no dust accumulation and so on. And since they use the large surfaces in the room, they create uniform temperature distribution, they reduce the vertical air temperature difference, which could be a problem, and also they reduce the risk of draft, because now you provide fresh air only to cover the ventilation requirements, or the fresh air requirements. So this is all very good, but I have just one slide summarizing currently what we know about radiant versus convective systems, let's say as hard facts. So there's been recently two review studies. The first one looked at the thermal comfort in buildings using radiant versus all air systems, and the second one compared more as in a field study of temperature and acoustic satisfaction in 60 radiant and all air buildings. So these are two review studies. And also in DTU there has been a study a few years ago comparing chill beams with a radiant panel, chill ceiling or radiant panels, and a slightly more personalized system for cooling, and looked at how people feel. So the results basically from the first two studies is that there is suggested evidence that radiant systems could provide higher or equal thermal comfort than convective systems. And the second let's say conclusion is that there is a tendency towards more, let's say, or higher satisfaction with indoor environment in radiant buildings. So as you might realize from these two bullet points is that they're very round terms, suggested evidence, tendency towards. They don't really say anything hard, let's say, or anything like we can definitely conclude about this. And the reason is that because at the moment, with the knowledge we have, we can't. There's basically some studies or some fundamental studies that is actually missing to compare directly what are, let's say, the effects on people of radiant systems and convective systems. But this is something we have to look further into. And as I said, there's a limited amount of literature on direct comparison. So this is, let's say, hard facts scientifically where we are. So just keeping that in mind, what we try to do within this study, within this project. We have demonstration buildings, as Eline mentioned earlier, and our idea in these buildings is to compare their performance, in this case in terms of indoor environmental quality, before and after the implementation of model predictive control. And these are our buildings, 2 office buildings, 1 elderly home and 1 school. So these are our demo buildings, where we will, or in 2 of them, model predictive control is already implemented, and it will be implemented in the other 2 as well. So our objectives is to do detailed long-term measurements of the IAQ in the demo buildings. And one thing in these buildings is that they have all, obviously, geo and taps, but they also have, let's say, a secondary system, which is in most of them the air-based system, the ventilation system. So when we do the measurements, we also want to see what is the real indoor environmental quality or the real temperature conditions versus the ones that are sensed by the building management system. That is usually the temperature sensor sitting on the wall. We are also carrying out periodic questionnaires, so that is the subjective evaluation of the indoor environment experienced by the occupants. And we also want to compare the physical measurements that we get from these buildings versus what people actually feel, what they tell us through the questionnaires. And in the end, we basically want to quantify the effects of model predictive control on IEQ. So that's why the before and after comparison. As you've seen in one of the previous slides, we installed a lot of different monitoring equipment in these buildings. And basically our idea, as I said, is to capture the thermal indoor environment, but not through, let's say, for a short time, but actually for very, let's say, long durations. And these sensors, they were installed in these buildings in last February. So we already have measurement of 1 year and 3 months, 4 months almost. So this is what's going on. I will not get into it, but in most of the buildings, what we are measuring, just to quickly summarize, we are measuring air and globe temperatures, or air and operative temperatures, depending on different heights. And it's usually at 0.1, 0.6, 1.1 and 1.7. These are the heights suggested by different standards. Then, since these are TABS buildings, we are measuring ceiling and floor surface temperatures. And we are also measuring the CO2 concentration in most of these areas. And depending on which, let's say, building or which structure you're in, we are also measuring, for example, window opening and some other things. So just to summarize, what we are trying to do is to get a complete understanding of IEQ and end user satisfaction in hybrid geotabs buildings with or by means of physical measurements and questionnaires. Provide suggestions for improving the comfort, health and productivity of the occupants, and the reason we can do this is because we have long-term measurements. But now linking to the previous slide, or to the where I pointed out what's missing, one thing is we also have to be careful about local thermal discomfort, because overall thermal comfort is basically right now what we're measuring. We're measuring the operative temperature in different places, but we also need to be careful about local thermal discomfort. Another thing is the effects of combination of different IEQ factors. So in this case, IEQ factors are basically thermal, air quality, lighting, and acoustics. And it's been very, let's say, understudied how their effects are and how they could affect, let's say, different perceptions. And one thing which we do not really do in this project, but it's important going forward, is that there's a need for fundamental research on the comparison of the effects of radiant versus convective systems. So that will be all for me for this slide, for this presentation.
Thanks a lot, Ongun. We will need you back in a quarter of an hour. Our next speaker is Qian. He is from Uponor, where he's kind of an expert, let's say, in sustainable HVAC and energy systems in buildings. And he is following up different research projects, among them European, among them hybridGEOTABS, and he will present now the TABS component within the hybridGEOTABS concept. Qian, you ready?
Yes. Thank you, Lieve. Actually, this morning we had a training session for the hybridGEOTABS, and there we present different design and details of the tabs, heat pumps, and ground source heat collectors. So there actually we have a lot of materials and it's recorded. So today I will present very shortly about the tabs. It's a global company that mostly covering Europe, East Asia and North America. So we now have around 4,000 employees and with the international markets. So the main business when it comes to indoor climate and solutions, we're manufacturers of different radiant heating and cooling solutions, tabs, cooling panels, geothermal energy centers, and of course boards and manifolds to connect this with the radiant systems, and also controls is a new direction we are also developing. So when it comes to the tabs, And I think Ongun has already introduced you a little bit the basics of taps, and I guess most of you are familiar with taps. So in conclusion, the tap is primarily used for sensible cooling and also as a secondary system or as a basis for heating. Also, taps doesn't overlapping with ventilation system, so in taps building you always need to design a ventilation system in order to have the good indoor air quality. So the application of taps, usually we use taps not in residential buildings, and we start with office or commercial buildings and also other type of buildings like educational schools, healthcare centers, and other kind of public buildings like museums and libraries. Here you can see a bit different references we have built, both mostly in Germany but also in other parts of Europe, about how this building looks like from reality. So, a little bit summary of the working principle of taps. So, we charge the building during the day and we discharge the building during the night. So, the temperature is controlled and we activate the building whole structure by the water. And of course, this is for the mild temperature. And if we come to more warmer temperature or more colder temperature climate, the outdoor temperature, we of course need supplementary system or secondary system in order to compensate and have the enough power to give the right thermal comfort. So this is some results. We can see that the dashed line here, for example, is the outdoor temperature. It varies, and if we don't have taps, this yellow line, you can see that of course it goes with the temperature variations of the outdoor temperature. But with taps, you can also see the switch of the temperature variations during this time, and it's becoming quite stable, and we can shift the peak. So the integration of taps or how we usually use taps, and this is also the concept of hybridGEOTABS. We have basically three key modules. The tap system, and this is usually designed based on the zones. So zone means that one zone you design and connect it with a manifold, and you can have different zones based on the load of your building case. Then we connect this with heat pump and also the ground collectors. So because the water temperature for the taps usually is very close to the room temperature. You don't go for high temperature heating or very low temperature cooling. So it's a good chance for you to use low exergy resources such as geothermal, and also solar can be another option in the source part. Yeah, a little bit information how we integrate for the taps with heat pumps, and we can have different mode, of course, to operate the taps. We can have classical heating or classical active cooling, or we can have both, or we can have passive cooling. We circulate water directly from the geothermal. So a little bit more engineering practice from industry when we introduce taps or how taps are constructed in reality. So when we're talking about taps, we mean that the pipes are embedded in the core of the concrete. And of course, in practice, there are different arrangements of the taps. For example, the second type, the taps with thermal socket. Here you can have a split water circulate. So basically, you have the water connected with the tap, also can be connected with cooling panels, for example, together to provide cooling. And in some areas, for example, if it's highly exposed to the solar radiation and you need rather different heat output from the taps, you can have a near surface system, which is very similar actually to the wet system of floor heating, for example. And also you can have more intensity of the pipes in order to have higher performance of the taps. So the integration of taps with a hydraulic system, I think Wim and Jelle will give you more information afterwards. So in general, we have, for example, two pipe system that the thermal socket is integrated in the taps water circuit, and this is usually aimed for the base load. We're covering the base load, and the rest are covered by the secondary system. And then we also have 5 pipe system, that the thermal socket is connected to the subgrid, their own water circuit, and this can be an optimal solution based on how you design it for the peak load structure. Yep. And also we recommend you to read the presentation and the records, recording from the morning, and I did it a little bit in the wrong order, but yeah, if you have questions, always ask me, not the question. Thank you.
Okay, thanks a lot, Qian. Then we have the third presentation of the first part, again Ongun from Technical University Denmark. TAPs are usually seen as a solution or an energy efficient technology for new buildings, and in this project we also wanted to look at renovation projects. So for this we suggest to use PCM ceiling panels, and that's the focus of next presentation.
Okay. Thank you again. So this one, as Lieve explained, that's the main point of this presentation. So the idea is to use ceiling panels or radiant ceiling panels that are filled with phase change materials as a renovation solution in hybrid geotabs buildings. So this was a very crowded slide in my previous presentation. And basically the idea of this slide is to show what are the benefits of radiant heating and cooling systems and why we are so much interested in them. And most of them, they related to TAPs, and some of, I will just mention some of these. The first one is that since they work with low temperature heating and high temperature cooling principle, they allow the integration of renewable energy resources, which you can find usually at the temperatures that you need in our surroundings. So it could be ground, it could be lake, it could be seawater, it could be other things. And as we discussed, it also allows transferring peak loads, for example, peak cooling loads to off-peak hours, and allows them to spread out, for example, over a day. And it also has, let's say, other benefits such as reduced total energy use and so forth. So what we are interested in is that when TAPs have so many benefits, we want to find a similar system that we can also use in renovation projects. Similar benefits and something that can be used in renovation cases, and not to limit, but also in new buildings. So that we want to find, let's say, something that can replace TAPs. And in this case, the idea or our proposal is radiant ceiling panels with phase change materials. That's the idea. So, very briefly, phase change materials can be organic or inorganic materials. And the reason that they're called phase change material is that you try to use it mainly within their phase change range. So, to benefit basically from the latent heat. You can use them passively or actively, so it means in one case you just have them in your room, for example, put in gypsum boards, but you don't do anything actively, or in the active case you want to control their charging or discharging behavior. That's a little bit like TAPs. It can increase thermal mass, if especially this is valid for lightweight buildings where you might not have enough thermal mass. In our case, we use it for temperature control of indoor spaces, management of the cooling load, and, as we already said, potential to use in lightweight buildings and in renovation projects. So, having said all these, our main goals is to develop a new solution that is basically phase change material or PCM ceiling panels to address implementation limitations and constraints in new buildings and in renovation. And one thing that's very important is to characterize the performance of these new PCM panels, because if you need a PhD or something similar to be able to use these systems, it will never get it into the market. So that should not be the case. So what we are trying to do is find out what their performance is like by climate chamber measurements and by parametric analysis through validated simulation models. So the new PCM panels, when you look at it, it looks very simple like this, nothing complicated, just a white box with integrated panels, integrated pipes. But I will not get into details, but we spent a lot of time trying to make this panel leakage tight So the idea is basically you have commercially available products, and that is the piping structure that is seen like this. The metal panels that are on the, let's say, lower surface and on the upper surface. And after you have this structure, the idea is to fill these panels with phase change materials. And one of the problems that we had, since we said these are commercially available products, so when they were built, designed, they were not, let's say, constructed with the idea that one day they should be PCM panels. So that was quite a challenge, trying to convert them into something that can contain liquid PCM. But we succeeded. We have made roughly around 50 of these panels, and the ones we have at DTU, they're the only examples of these panels. So they're only there. And since we said, okay, the panels very good, we want to see how they work, if they actually can be a possible alternative to tabs. So we chose a case study. This is DTU's campus, Technical University of Denmark, and we have a recently renovated office room that is basically like an open plan office for students. It's about 53 square meters, and it's designed for 24 students. There are never 24 students, but it's designed for that. And this is basically the layout of the room. And this is what it looks like basically if you had a panoramic view. So the interest of doing this is because there has been a claim that PCM ceiling panels can work like tabs. So when we started doing these studies, we wanted to find out if they really can. So we have these panels, so we created a simulation model of this office or the open plan office that I just showed. So what I'm going to show is simulation results, and they're from Transit 17. What we did is that we made the assumption that, okay, we have this room, it's designed for 24 students, there are corresponding lights and internal heat gains and so on, and we made different designs. And in these different designs, this room was cooled by PCM ceiling panels, by an all-air system, and by tabs. So simulations allow you to do that very easily. It's a little more complicated, obviously, in reality. So these are the results. The result is first for the primary energy use for the cooling season. In Denmark, it's from 1st of May to 30th of September, and this is as I said, the energy use. So, and it's divided basically into the actual, let's say, fans, pumps, and the cooling energy. And when we look at it first, when we look at this graph, what we see is that that both tabs and PCM, they have very similar total energy use values, and they also have about 15% lower energy use compared to the old air system. And if you look at between the PCM and the tabs, if you look at the distribution of the energy use of different components, you will see that they are very similar, the distribution of these values.
Excuse me.
Yes, please.
In the study, the control itself was RBC, or what was the RBC?
This is plain RBC. There is no MPC in here yet. Okay. Yeah, but thanks for pointing it out. So this was basically the overall energy performance within the cooling season. Then the next one is, because we say that when we did this study, what we want to focus on is energy performance, created indoor environment, and how they remove the heat from the indoor space. So this one is basically looking at, again, the same systems, but trying to figure out, or basically showing how they remove the heat from the room. So how much the air system removed heat from the room, how much the floor, and how much the ceiling surface removed. And again, the three systems. So in all air, it's basically almost 80%. There's some, let's say, some heat absorption from the floor and ceiling, but nothing activated there. But if you look at the tabs and PCM, about 30% of the heat was removed by the air system. This is slightly higher than what we wanted, but it's because since it's for 24 people, a very high occupancy, there was a need for a very high ventilation rate. But that's not the point. The main point is that in the tabs case, the ceiling removed about 55% of the heat from the room, and in the PCM case, the active part where the actual PCM ceiling was, it removed 50% of the 50% of the heat from the active part. So it's again quite close or quite similar how they remove the heat from the room. So very good. These are all, let's say, overall values. Now the second one is more related to, or third one is more related to indoor environment. And this is again the entire cooling season. So this is from 1st of May, 30th of September, and these are divided into categories in one of the standards that we just heard in the keynote, EN 16798. So these are the categories given in the standard 1, 2, 3, and outside the 3 for the cooling season. And basically, yes, please.
Maybe you said it, but I didn't. Did you cover the whole ceiling with the PCF panels, or
No. Good, very good point. Normally you don't have enough space to cover the entire ceiling because you have lights, you have diffusers, and so on. In this case, it was about 50% of the ceiling, so not the entire. Normally, what we see is maximum you can go with is around 75-80%. Then maybe you have more detailed knowledge, but that's like maximum we can go with. So in this case, it was 50%. So yes, so this is looking, as I said, in the different categories of the thermal indoor environment, but overall indoor environment according to this to the EN standard. And in this case, what actually we can see is all systems were quite similar, except that the PCM, it slightly had, let's say, more hours in category 3 and category 4 compared to the two other systems. And in this case, we already saw it with the simulations, is that PCM at the very, let's say, some peak periods, it had limited heat, let's say, removal capacity. So this was kind of expected. But one thing I should say is that when we were trying to do this, because it's tricky to compare the systems if you, let's say, try to fix one temperature set point because they work differently. What we tried to do is, now you can see it maybe didn't fit, but we tried to achieve for all systems 90% of the time in category 2. That was our, let's say, baseline. Now you can see that it didn't, let's say, end up there, but it's what we kind of expected. But that's how we justify the comparison of different systems based on the same or similar indoor environmental quality. So this is the overall picture. Now, another thing I want to show, in the previous presentation, I mentioned that all air systems are normally have a set point and they try to control the temperature on the deadband. And we said that the radiant systems, or with tabs and high thermal mass systems, it can spread out a little bit. So what we see in this graph is it's basically a duration curve during the entire cooling season. And what we can see is that in all air system, they are more, let's say, concentrated around the temperature set point, and in tabs and PCM, the temperatures were more spread out compared to the all air system. So this is linking to the previous presentation. So we are doing some ongoing work. We have these panels installed in the ceiling of a climate chamber that we have. We've set up the climate chamber as a 2-person office room. These are simulating persons, we call them dummies. They have 2 computers, there's light, and this electrical heating mat is basically simulating the window surface. So we have, this is a detailed view, and this is the panoramic view. Our idea, what we're trying to do right now with this climate chamber, is that we're trying to figure out basically how these PCM panels, how they work under different cooling loads, under different flow rates, like water flow rates and supply water temperatures. And basically what we are trying to get is basically some graphs that can basically help designers to have some quick idea of, for example, how much of the ceiling they might need to cover for a certain cooling load, or what should be with different, let's say, flow rates and supply temperatures, and so forth. So to summarize, again, it was a simulation study, but we showed that the PCM ceiling panels do work like tabs in terms of energy performance, thermal indoor environment, and heat removal performance. They can provide similar benefits to tabs, applicable in renovation of buildings. This one I didn't get into, but this is something we are doing extra on top of this PCM work. We basically have solar panels, photovoltaic and thermal panels, and we are trying to basically use them as a cooling source during the night. But they're not directly coupled to the PCM panels. We have separate loops, and there's, let's say, water storage tanks and so on. But again, we want to see what is the potential of this, because it's something that is, let's say, renewable. And now, last point is a little bit more like, there's been a lot of research in PCM. It's not like one of the first ones to do. But what we see is there's, let's say, lack of working examples or real field studies that's installed, measured for a long time, and you can see that it works. So to overcome that, we need design, dimensioning, and control methodology. So as I said, if you need a PhD, this will never get to the market. We need working and successful examples. Together, we need long-term measurements. And the last point is the economic analysis. So I never mentioned until this point on purpose, because this would be very important if you really want to get them into your building. So we did an economic analysis based on the same simulation study that I showed, and what we can see based on, again, all air tabs and the PCM panels is that the tabs is always, when I say always, for different cooling loads, cheaper than the all air system. PCM is more expensive. I acknowledge that, but not as you might think or hear, like double, 3 times or something. What we found out that it was 5% more expensive under the highest cooling load. So it might not be as bad as we initially thought. So having said that, I will conclude my presentation, but I would just like to acknowledge some of my colleagues and obviously our project. So thank you very much.
Thanks a lot, Ongun. We keep the questions for later. I have at least some. So up to now we focused on the taps, the primary heat-cold distribution system, but in the project we look at hybrid geotabs, so we have a supplementary system and then some design challenges pop up. And in the last part now we have kind of a dual presentation, if I understood well, of Wim Boydens and Jelle Laverge. They are both connected to the University of Ghent in Belgium, but Wim is, I think, here in function of the CSTO of Boydens Engineering, so he will explain you what they would like to have in practice to design a hybrid geotabs building, and then Jelle will answer these requests by the methodology we are developing within the project to try to get to these requests from practice. Okay?
Thank you very much.
Okay, it's a title that promises a lot, but it's more like a title that should show the challenge that is in here. You all seen what hybridGEOTABS is, and in the early stages of a project where you try to assess the concept, where you try to convince a developer, an architect to use this concept, which has multiple advantages, as Ongun said. But then the real challenge becomes how can you qualitatively in the early stage, when not all details of the building, not all details of the underground are known, how can you give some figures and good estimations on the performance? That's of course always impossible. There's always a gap. But you want to compare it at least to give it a fair comparison with other concepts. And then it becomes still a big challenge, because in most energy performance assessment methods, the specificity of the geotabs, of the hybrid and of the control, even if it's RBC, it's very hard to fit it in any assessment method. So that means that even if you're convinced of the advantages, the moment somebody around the table in the early design phase asks, well, what is the benefit for me now if I choose this system? Then you're confronted with a lot of work where you know that the relevance, okay, it's somewhere there, but it's only used to convince, and it's not given any evidence on, okay, if you use this method, you compare these systems, this is the difference in quantified advantages. Yeah. So this is a little bit, so one of the challenges to remove this barrier, and one of the goals within the project, was to find a method trying to get all sources, could be measured values from existing projects, could be data from simulations done for projects, could be data produced by simulating a lot, that we use them to try to get an easy and a fast tool for designers to give an idea what the performance of the concept could be. That's one thing. And the second is, like, if you have a hybrid, you always have a choice, like how much hybridity is in there. How much will you rely on the geotabs, and how much could you rely, or do you have to rely on more conventional installation? Okay, so it's like to help decision making in an early stage. And Lieve, one of my staff members, she said you should read it as to hybrid geotabs or not to hybrid geotabs. Okay, but that is not really the question. So if you talk about hybrid geotabs, you already want to geotabs, but you want to know in how far. Good, so give it a fair level playing field in that early project design stage, in that early concept decision stage. And we've already seen there's an interaction of a lot of things, storage, we have advantages as grid flexibility, we have a lot of elements that are very hard to quantify, and certainly in a very early stage are almost impossible to quantify if you only look at the project itself. So, every building deserves a share of taps. We've seen that today already. And the main question that my staff member Lynn also picked up well in our discussions, the question is, or the answer is, I have a project and I want to apply geotabs. That's not an issue. It's not should we or shouldn't we. No, we see the advantages. We know they're not all quantifiable. We know we want to include it. If we have a building, we have a slab. For each square meter where we walk on, we have a slab, unless it's some cowboy wooden construction. And we have a cooling demand and heating demand, unless we're in the desert or in the North Pole. So you know we can use the advantages of the geothermal combination with taps. So and that's really, I want to apply the geotabs. It will be a hybrid, and the question is in how far. So what will be the level of hybridity that for in an early phase my project could have the best advantages? And I would like to have a way to quantify the advantages of this hybrid related to the classical ones, like Ongun said, the all-air, or even the PCM panels, why not? To show what is the advantage that could give the client a push to say, okay, I'll invest in this. This looks good, and this does not only look good because it brings money, because there are other decision elements in it. It could be that the sustainable aspects or the future-oriented aspects, they fit into the company's DNA. It's not only about looking for the low-cost solution over a longer period. It's also over some. It's also including some values that you have in the project that do match with the client's DNA. Okay, so what I want to stress here is that the level of detail in that early phase is not very accurate or detailed. So we're talking about building level information characteristics. That's the only things that are known. And there is some drawing of an architect, but he listens to the designer to hear what should I do with my windows. Do I need more? Do I need less? Do they have to be very performant? Do I have to have sun shading? Yes or no? And it's not so easy to answer in a geotabs building if you would rather have sun shading, yes or no, because if you have a cooling dominated building, it's clear. But if you have a heating dominated building, you might be better off without sun shading. Okay, so there's little detail in that phase. And also for the pre-design phase, where pre-design for me is to quantify how much geotubs and how much secondary system we need, a quick, a rough and a simple method with all the elements that we know in that phase. So that's to situate a little bit what do we know at that stage of the project. We know what the building will be used for, we have an idea about geometry, we know how big it will be, how much floor levels it will have, we know in what climate, what city it will be built, we might know the legal frame. So we have some elements that could already be enough to make a good assessment on the level that I was talking about. And we know that there could be some constraints, like how much space do we have under the building to put the geothermal borehole field. So there can be some constraints. Those, of course, you take into account already in that phase. Okay, so it's not only a calculation process, it should also be having elements that create a decision-making process and a fast one about, for example, emissions, about, for example, the energy use and the type of energy that you use. So the cleanliness of the energy supply to the energy concept of the building. So that we would like to transform in guidelines and in tools, okay, for that early stage. So I'm going quick through the framework, and then Jelle will try to show you how the underlying buildup of databases and splitting methodologies will, together with this framework of tool, give designers the possibility to pass by that early design stage in an easy and feasible way. Good, so we have information about the building. The first results that we would like to have are mainly on energy demands and the peaks or the powers that we need for such an inert system. And we would like, with post-processing, because we will do it for Europe, so we need variables that are dependent on the location of the project, that we can post-process. Okay, what will be the CO2 emissions, for example, depending on the energy mix in a certain location, that we have the constraints about legal frame for geothermal drillings that you could or could not do and towards a certain depth. So we put that all in the post-processing phase. The costs also, like what are the costs in Poland, what are they in Brussels, what are they in Madrid. So that is a part that can evolve for the coming decades and stay correct. And the results coming from the building exercise, they should be, except for the climate change, they should be rather correct and stay correct. Okay, so we define a building. We try to do it with the basic characteristics that we have in that stage. And Jelle will explain how we will get to it, but building up a database, we would like to have a quick, how would you say, a match with some pre-simulated projects to extract the results, being the demands and the peaks. And also within the project, looking for a splitting algorithm to have the demands divided in secondary and primary system, and also the peaks, how do we divide them. If we have those results, rely on databases from practice that have to do with the cost for the system, the cost for the energy, cost for CO2, for example, and that we will post-process towards an easy readable element. Not only we will do it, but mainly the partners in the projects, and that's Geoter from Spain climate consult from Switzerland, and us Boydens Engineering for, let's say, Brussels and surroundings. And also Uponor will have input on prices of systems so that we have a good spread over Europe of this tool. This is what it could look like. So you see we're basing ourselves on databases that are built up. The most needed ones are built up by University of Ghent. The ones who have to do with market values, with feedback of practice coming from the industry partners. And we want to come to an easy to use tool to assess the performance. So you see again information that you can put into the model, or not the model but in the sheet, that we see what the demands are, and that we have the information that we defined that will help to decide in the project if it's a feasible or a not feasible solution. Okay, I'll go quickly through this. The databases that are the core or have turned out to be the core of the methodology that we're working on. We also had the idea of, okay, if you have a building, you have the basic characteristics, can you not just find an algorithm without a database? But this is something still to be worked out. But we'll make the database. We'll make sure that each point in the database has unique identity and all the characteristics are clear, so we can use those characteristics to compare or to correlate with the new project that we will use the tool on. So this is what should come out as a minimal element. It's more than this, but basically we're thinking about the power peaks that we need and what we would like to be delivered by the primary and what by the secondary system. It will be also subject of a splitting algorithm that has been worked on by the University of Ghent. We need the powers, of course, and now one of the challenges for us and within the project is like you can do an optimal control. Should you think about, okay, this building will use an optimal control, model predictive control is not read and not yet enough market ready to say, yes, you have to do the assessment thinking or assuming the model predictive control is installed. So this is a little bit too soon because we're already deploying those buildings for some decades, and we don't want to get an early stage assessment that is too positive and that will be accomplished in 5 to 10 years. So actually the mismatch with what is the potential in reality, we would like to have that reflected in the tool. And that is why we're kind of RBCing the situation by estimating what water temperatures will be normally expected each month of the year for a building. So there you need some experience from designer, or if you have no experience, some gaming of the designer to see like, what if I change a little bit the core temperature, what is the effect on CO2 emissions, what is the effect if my hybridity changes on my assessment criteria. Good, so a lot of data, of course that's a huge work to do, but that's about the only way to get practical information for the people around the table, including the designer, the project developer, the architect, to show what is the impact, what will be delivered each month of the year. In a rough estimation by the geotabs, what will be delivered by the secondary systems, and you can see it each month of the year in cooling and in heating. And this is enough to do with some further post-processing to get all the criteria. Could be financial, could be environmental or ecological, that can bring the people around the table to decide on using hybridGEOTABS and what hybrid level that it should have.
So, as Wim said, at Ghent University we're basically working on whatever goes into the background of the design tool you just explained, and that's mainly based on an analysis of the building stock for the different types of buildings that we are dealing with in the project. And for those of you that were not in the training course or are not familiar with the project so far, we are concentrating on 4 types of buildings. You already saw the examples of the case studies we're working on, so it's office buildings, elderly care homes, schools, and large-scale housing buildings. So, like Wim explained, we want to have a database of data that describes buildings in each of these 4 categories. And so we have a workflow that looks more or less like this. We do a building stock analysis. From that we extract modular archetypes for each of those buildings. Then we use those archetypes to do a geometrical fitting process to the basic data that we have about the composition of the building stock. From that we run building energy simulations that get us heating and cooling demand profiles over the year. And from that we can then do all the calculations that Wim just introduced. Just to get an idea about how this works, this is the archetype that we use for the office building. So we made it modular in such a way that we can stretch the archetype to match volume, floor area, heat loss surface characteristics of a building. And we start from an analysis of higher than 1,000 square meter office buildings in Belgium. We look at the range of what has been built over the last 10 to 15 years, and from that we then sample a range of buildings to come to a database of buildings. This figure has partly disappeared, but basically we not only look at the data from the building stock that we get from the government, but we also look at the backlog of projects realized by our industrial partners. So Boydens Engineering has realized lots of buildings over their portfolio that is distributed among those functions that we are studying largely, so that is a very good way to start. We do similar analysis with Lemon Consult and with Geotar, and so from that data we also look at what are the distributions of heating and cooling loads that have been calculated for these buildings, what are the installed heat pumps sizes related to that, how was the sizing of the ground source heat exchanger, and from that data we then try to extrapolate to typical sizing numbers. For example, typical installed length of heat exchanger for different types of buildings, for different sizes, and also based on that cost data. Yes?
Basically, you're just trusting that the designers did a good job initially.
Well, I'll get to that, but we're doing 2 things. So we're looking at what is typically in the market, and so what has been realized in the past, and we're also relying on simulations to extrapolate from that. So it's a combination of both. So from that, we're also extracting cost data, which you need to then do the economic analysis. For example, installation cost of the vertical ground source heat exchanger. And then, okay, this is our raw data. Now we need to go through the process of making this reliable input for the design tool. So there we follow a number of steps. So first of all, we standardize this information into a number of standardized documents for the different building types, one of which is a standardized hydronic scheme. And then from that we start doing the predefined steps for the design method. So this is an example of what the standardized hydronic scheme looks like, so that we can fit this to all of the projects that we're looking at, and also use to set up the simulations we are running. And so the process then looks like that. We start from the general building data that we gather, describing mainly the geometrical characteristics of the buildings. We create a detailed building energy simulation model from that we then run, which gets us load duration curves and heating and cooling demand curves for those buildings. We don't do this once for every building, but we do a variation of the physical parameters of the building based on typically varying things such as orientation, climate zone, internal gains, thermal mass, envelope and shading characteristics. And so we need to define all of these parameters that we want to vary and the levels that we want to study. And so it has already been said by Eline. We looked at what are the typical zones where construction happens in Europe. So this is a map that shows where the population is in Europe, and this is a map of the climate regions. And so by combining those two, finding the biggest market, we defined 3 interesting climates that we want to look at, which is Madrid, Brussels, so Madrid, which is representative for the hot climates in the south, Brussels, which is like the temperate region, and then Warsaw, which is more to the east and more representative for a cold, slightly Nordic climate. So these are the things that we're looking at in terms of climate. The variations in terms of properties of the building envelope. So we did an analysis of the typical U values and maximum U values that are applied in different countries in Europe. And so based on that, we also defined 3 levels ranging from let's say somewhat older buildings in the temperate region and typical building in hotter climate regions to what is now typical building standards in large parts of Europe, and then a more ambitious level close to passive house standards. And then we also define scenarios for occupancy, internal gains, controls for shading and things like that. And so what we do then is introduce all of these in the simulations. This gets us profiles for heating and cooling demand, which we can then use to create load duration curves on which we can base the sizing of all the components, which is then used as input for all of the information that Wim just presented. And to make it a bit more tangible, we are now working on doing some clustering of all of this information into typical configurations, so that in a very early design stage you can rely on rule of thumb figures that come out of this, that are based on the results of this larger database. As this is all based on simulations and post-processing, we also set up a let's say verification procedure. So if we create a heating and cooling demand profile from a simulation, then do the sizing of the system based on that as a check in a subset of the results. We then reintroduce the power and heating and cooling power that we predict into a simulation with the same thermal properties, and verify that we indeed realize the thermal comfort bounds that we started with. Okay, so this was a short background on
what we are doing to support the design tool. And I think, Lieve, now it's time for questions.
Yes, we are open for discussion. I hope to end at latest 6 o'clock, let's say. I don't think we're not too late. I suggest the speakers to put yourself in the front because it's you who have to answer. It's not me. So, are there any questions from the public? Please.
Is this design tool ready, or are you still working on it?
We are still working on it.
You are working.
Yes, so it's the end product.
I suppose it will be available on the website.
Yes.
This is the procedure for Horizon 2020. You have it available. So you are in the 4th year of your project.
We are starting the 4th year after the summer.
Okay, so it's still early to have it ready.
Yeah, and the goal is that we develop a new Riva guidebook. So there's a Riva guidebook.
A new one, not the old one.
Yeah, so a new one that focuses more on the designing and operation of hybrid geotabs, because the old one basically introduced the geotabs concept.
Descriptive.
Yes, and we want to go more in detail on how to actually design such a building.
And one more question. Do you consider foundations and foundation walls?
Slab heat exchangers, you mean?
Yes, as tabs.
No.
Do you take them into consideration in your project, or you work only above the, let's say, ground level?
Yeah. Also the ground level, but that's then the bore field. That's closed heat exchangers, which are typically the U-tubes in the underground, not in the slabs.
But not foundation piles, not foundation walls, you don't take
Are
them
not included. They are included in a geotech project.
I know.
Okay, you can have a look there.
But the focus of the project is not so much on the different types of ground source heat exchangers, it's more on the integration of a ground source heat exchanger. The main focus is on double loops, but the integration of ground source heat exchanger, control, taps, and the hybrid, the secondary system. So.
Last question.
That would have an impact on the cost evaluation, the assessment, but then it should be changed afterwards. Price database.
Last question. How do you persuade architects to implement such solutions in their masterpieces?
In the masterpieces.
Masterpieces.
Masterpieces, okay.
Space utilization might be another here. The fact that you don't need to put
I mean, because usually architects are pretty reluctant to any, let's say, integration and working together with structural engineers and mechanical engineers and HVAC engineers and so on.
Maybe
so
I can give you
persuade them?
I can give you some practical information. When we had the discussion with architects during a real commercial project, it's not research project, but commercial project. So the thing is that when we get the customer, for example, we want to build a building that is the office. Then of
you
course,
go to certification.
Well, that's one important step. But your question is more about how to convince the architect, the artist. So one thing that we're
very good point.
So because I guess we all have an engineering background, so we focus on different
architect stuff.
Well, I would introduce a little bit more because it's like two people, they don't know each other, but we need to understand each other's values. So what do you put priority on your work? What do you like? What makes you excited? So for engineering, we take a lot discussion on efficiencies and energy savings, sustainabilities. Of course, this is important for architects in their career development in order to have your design that is sustainable and fits the certificate, for example. But the thing really makes them horny is that my design is very clean and very innovative, and they don't like, we have this discussion many times, they don't like pipes, they don't like vents, and they don't like seeing all these radiators around. This will kill their interests. So taps has an advantage that you put the pipe.
hidden.
It's hidden. So when you come to a room that is in the morning session, I put the picture that how a TAPS building looks like, the moments when architects come into. So basically it's just a space. Now you can have all your freedom to decide how you want the things, especially when it comes to different things that, for example, TAPS buildings, in reality, there are a lot of glazing areas. So architect wants to play with the light. So this is very important. And in TAPS buildings, actually you can achieve this rather than conventional buildings. And another thing is that when we have the wings of the buildings, you have different geometries. And TAPS can also provide different solutions when it comes to wings. So you can have different orientations and the shapes, and this makes them feel a bit happier. And another thing is that we did the test in a commercial building in Germany that the building was designed with 8 stories. But when we have TAPS and this limited ventilation system, you can have 1 more floor. So in the end, it's 9 floors.
Yeah, but even there, an architect who is really reluctant could not be convinced.
Yeah, of course.
So
there are always discussions, because even though the architect accepts the TAPS ideas, and there are a lot of coming back and forth. No, I want to. It's not easy, but this is a business, and it's applying to every.
I think you have a menu of about 30 issues that you can use in the first discussions with an architect to convince him.
This is the deliverable in this inspiration?
No, but I can make it if maybe I write a book. But it will be somehow also inserted because it's a very
6.4.
6.4.
Actually, in context of the business model, we are looking to the values.
Yeah.
And another one is the more limited utilization of space for services, not only in the rooms but also in the technical rooms. So we actually have.
Yeah, but it will not be the prosa that you can use in the conversation.
Also,
but
we need people.
I think in the former one, in the descriptive one, there's more.
Explanation.
Like okay.
Yeah.
Yes. They might have been distributed because my contributions were in each chapter a little like okay, so you'll have to gather them together, and you'll find a lot of them that an architect will understand. Yeah.
What is this chapter? What stage are you now?
So basically, at this point, we have the simulations for the office buildings done, more or less. We have a splitting algorithm that then processes the heating and cooling demand, taking into account the design of the taps, the desired comfort range and things like that. And so we have analysis of the costs, and we are now in the process of bringing everything together and being able to do the clustering towards more simple rule of thumb.
Because you know, cooking is only when it's tested and also.
Yeah, we have to do sanity checks also.
Yeah,
And then that's what
that's the goal, but yeah.
I think it was in the first presentation it was based on the building type, and it was specific on building did not have the residential.
So there's a difference between the demonstration projects that we showed in the first presentation and then the goals of the whole project. So the whole project has the 4 types, but because at the beginning of the project we needed to quickly find the number of buildings where we could do demonstration, there was no buildings available through the different partners that had a secondary system and were residential. So we have a case study that is residential. It's in Switzerland, but it only has taps. It does not have a secondary system, so we could not implement the controls that try to better balance the action of the secondary system and the tap system. But we monitor it anyway, and it will be included in the reporting of the project. We also do some work on indoor environmental quality measurements. Yeah, but we cannot implement the NPC because there's no secondary system to play with.
You can always use secondary system.
Yes. But then the tenants may not be easily convinced of that. That's also a problem working with residential buildings. There's much more stakeholders to convince.
Having a design tool, I can imagine that just gathering of all the data and again, comprehensive, extracting the key components would be beneficial not only for designing geotabs, but also designing other things. Is there any effort to make it available, or are you trying to use it just for the geotabs and will you integrate well?
Oh no, we're also collaborating in an international energy agency project called Annex 70 Energy Epidemiology, and there's a lot of partners involved there that are focusing on building stock analysis for different typologies, and so the more generalizable results will eventually be part of that work.
Is there any outcome to this?
Also there we're starting the last year, so it's crunch time for that.
And it's 4 years project.
It's a 3.5 years project.
Do you have a clear view already on the minimum input data you would need for the early design stage too? For example, can you just work with monthly data coming from a monthly energy balance method in EPD?
Oh, we didn't even go that far. Like the input data from the project side would be really characteristics of the project without having made any estimate of loads or load duration, or just really thinking, okay, what are we going to do? What does the project look like? A first sketch of the architect, then trying to assess those characteristics.
So it's mainly building geometrical data, the volume, the floor area, the location, the type of building, is it an office, an elderly home, the overall U value, glazing percentage, so the real very general data. And actually we combine those with, via the database, we combine those with all the dynamic simulations that we are doing in the building stock analysis. So you don't have to make a simulation. You can just give the input data and we find them the closest by building in our database that is then started from for the sizing. So that's why we vary also a lot of building sizes and shapes and these 3 ranges of U values and so on and so on, to be able to find the one that is closest to what you need.
And that's actually one of the main goals of the project. We really want to be able to do this with as little information as this, because as Wim explained, the goal is to have some basis in the really early design stages where you don't have the time nor the resources nor the information to do much more actually. So you just want to have some early stage predictions, like in the range of this is what we estimate in terms of investment costs, in terms of sizing for both of the systems, the different components of the systems.
Somehow replacing the more than 2, 3, 4 meetings with all the stakeholders to convince them there's something in this concept that really matches with your ambitions. That takes too much time, and if you then have to prove it and have to calculate it, then really as a designer you say, why am I doing this? And you see the advantages are on several levels that you could call societal steps forward. That will use more the electrical grid. It could be greened faster than the other ways of heating buildings. So you have all those advantages, and you need a tool to bring it to the table in an early stage. When you go towards further stages and you have the EPBD that is calculated, then you're even more lost. Because then you have to prove this does not work correctly for this concept. So we want to deploy it, that's the first thing, okay? And we don't want this to be built just on shoulders of diehards, because they will die after a while.
I'm just wondering, since you have this multiple buildings, are you just reflecting on, in this case, this hybridGEOTABS delivers so much and it costs so much, or will you also look at other design features and say, for example, you should alter your window-to-wall ratio or U-value and you can come up with an even better design, which is even more cost-effective. Is that also how you will approach it?
Okay, there's a part in there on the building level that will be feasible with what we do here. We need some set point adjustment then, I think. But certainly on the basis of the cost data, on the experience out of other projects, it's not only hybridGEOTABS that the designers or the practitioners do who are in the consortium. They're not building their business on hybridGEOTABS. They're doing a lot of energy concepts. So we have the data for the different concepts so that we can compare. That's what we try to do.
For the building, you could change the property to yourself to another amount of glazing or another insulation level, and then we'll find again the building that is closest to your demands, and you can compare. In one case you might result with more geotabs or lower costs or higher costs than in another one. So in that way you could... No, within the tool it search what is closest to what you want, but you can think yourself, okay, if I make my building, if I change the orientation, if I do this or this or this, you can play with the parameters and we'll find the other building in the database that is closest to that. Because for each geometry we have all these variations, so you can actually start playing with them.
Also, there's a sensitivity analysis that you can do that basically is provided because we have the information available. But further to your point, it's actually a conscious choice not to just do an optimization, because then it's really restrictive on architecture. And so to come back to the very first question, the goal of the project is to demonstrate that every building deserves a part of hybridGEOTABS. And so also, if it's not the best glazing percentage, but for some reason the architect wants this, then you should still be able to provide the good information for that.
If you optimize the building design towards geotabs, then you'll have an ugly building. And probably not comfortable on all comfort issues. So the daylight so we've seen examples through the past 2 decades. So that's not the aim anymore. On the other hand, and that's maybe an answer also to the first question of the Mr. there, is that if you use a geotabs, you'll have to do it right from the beginning. And it's an integrated design, an integrated approach. Architects like that. Like it's an integrated design. They love it. They don't know what it means, but they love it. So you already you integrate in your building design a part of renewable or potential renewable for the future, depending on the electricity grid. So once this is in there, you can upgrade it later. So this is one of the main reasons that you don't only put a building, you are compliant with the EPBD, and then you have a minimum share of renewable, you put some PV on the roof. That's not the way to build the future. So we would like to have the integration and the affinity for integrating such systems very early in the concept approach.
I have a question about PCM.
Yes,
3 small questions. You said, or you showed that the temperature distribution you have, drifting, let's say, with the PCM is larger than in the other cases, slightly.
In the air case.
In the air case, yeah. And you also showed that the capacity for heat absorption is lower. Has this to do with the power density of the PCM?
It has to do with very high cooling load, like off the room, and then maybe not enough PCM amount itself. So
the thermal conductivity is too low.
Right. So that's another issue. But so
it's an important issue.
yeah. I mean, it's one of the main problems with the PCM is that. But in this case, we did 2 cases. So we actually did this study just when we were, let's say, in parallel when we were constructing the panels. So as the material, the PCM itself, it has 0.2 watt per meter Kelvin. The one just like raw material itself. But we used in the simulations 1.2 because in literature we found a similar panel construction. So we said, okay, well, this structure that, because they had also some metal panels, fins and so on, it's very similar to this structure. So we said, okay, now we will go with 1.2 watt per meter Kelvin. So it's increased and we could actually see a lot of difference. But the problem is this room, as I said, it's 53 square meters, and these simulation cases were for 24 occupants, so it's about 2.5 square meter per person. It's very, I mean, normally an open plan is like 10. So, and it was 50%, so there was some limitations
in the worst
there.
case simulation.
Yeah, yes.
And then regarding simulations, the operative temperature, we usually say it's the average of the air temperature and the radiative temperature. Does this still hold for taps or PCM ceilings? Can we still say it's just the average of both?
Well, average is kind of simplified actually, because normally you should take into account the convective and radiant heat transfer. So or the coefficient.
Are you also just take the average?
No, we did we basically used the output from the software, but the software uses the ones with the heat transfer coefficient. So the software does not automatically do the average.
I'd be interested to see the results.
Yes.
What's then the weighting factor for the
Sure.
components? And regarding the heat transfer coefficient you have from your ceiling to the room, is there any new insight?
Yes.
Okay.
Yes. I just no, but you mean for the ceiling cooling case, just for me to understand, or
For the PC.
you mean but from the surface to the room, right?
Yeah.
So yes, and the update or the new insight is that it's not directly related to the project, but it's related to something else. So for the radiant systems, and if you look at the heat transfer coefficient, it's what you need to provide to the room or what you need to remove from the room is actually independent of the rest of what's happening in the back of the surface, because the heat transfer, let's say, interface is the surface. So you have, let's say, the room side, which is interacting with the surface temperature and, let's say, surrounding air and the other surfaces, and there's the rest of it, which is the room side. Then it's important if you have radiant panel or tabs or other systems. So in this case, we basically treat it as a normal radiant ceiling panel. So it would, under ceiling, let's say ceiling cooling conditions, it would be, let's say, just 11 watt per meter Kelvin. But then it makes the assumption that there is natural convection, because then normally out of that 11 you can say, okay, 5.5 is around radiant, and then the other one is, let's say, the convective. Now, two things, because the first one is that makes the assumption, as I said, that there's natural convection. So if you have a diffuser that could be, let's say, a linear slot diffuser or something else, if that blows, let's say, the air along the ceiling, then it has the potential to, let's say, to move it to the forced convection zone. So you will have a higher, let's say, higher heat transfer coefficient. And that is something we want to try in the climate chamber experiments. Because in the climate chamber right now we don't use any ventilation. It's not realistic, but we first want to know what the PCM panels can do, and then we will look into different cases with that. The second point was that we, as a part of a separate project, we recently did a review of surface heat transfer coefficients of radiant systems. So for floor, wall and ceiling, and all for heating, cooling applications, because our feeling is that it's very important for radiant systems, because it's as I said, it's the interface between the surface side and the room side. but we kind of have the feeling that it's overlooked a little bit, that it's just taking for granted whatever and simplified a little bit. So we did that, we looked at the standards, different studies, guidelines, because not everything is the same, and we see that depending on which application you use or which coefficient you use, there could be quite high differences, which is, I mean, expected, but it was not quantified before. So, but in the paper we kept it to natural, because if you get into force, then it's like another world. So we didn't move that.
Are there any other questions, remarks? I think it's about 4 questions.
We should actually finalize so that you all can go to the dinner tonight. Make your black tie.
It's black.
Okay, then I would like to thank all speakers for